Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a gentle and curious idea that has been quietly growing in modern physics, the possibility that another reality may be intersecting ours, not with drama or explosions, but with the lightest of touches. Before you settle in, I'd love it if you could take a moment to like this video and subscribe, only if you truly enjoy these slow, unhurried explorations. And when you're ready, feel free to leave a comment telling me where in the world you're listening from and what time it is for you right now. It's always a comfort to imagine all of us scattered across the planet, listening in our own small corners of the night. Now, you might want to dim the lights, let the room grow a little quieter, perhaps turn on a fan or rest your head more comfortably. And as we begin, remember that there's nothing here you need to memorize or understand all at once. If your mind drifts, that's perfectly fine. The story will keep flowing gently, whether you're listening closely or floating somewhere between thoughts. Tonight, we're not searching for shocking revelations, we're listening for whispers. Reality most of the time feels reassuringly solid. You place a cup on a table and it stays there. You look up at the night sky and the stars hold their positions night after night, as if they've agreed on a script and refuse to deviate from it. Gravity pulls downward, time moves forward, causes led to effects. It all feels dependable. And yet, throughout the history of science, progress has rarely begun with comfort. It usually begins with a faint sense that something doesn't quite line up, a tiny irregularity, a result that's just a little off, a pattern that works beautifully, except in one quiet corner where it misbehaves. Think of reality as a calm lake at dusk. From a distance, the surface looks perfectly smooth, but when you kneel closer, you begin to notice small ripples, a breeze you hadn't felt, an insect touching down, a stone dropped far away, sending gentle waves that take their time to reach you. The lake is still the lake, nothing is broken, but it's no longer perfectly still. Modern physics has been kneeling at the edge of that lake for over a century. At very small scales, the world refuses to behave like the solid place we think we live in. Particles blur. Certainty fades. Objects seem less like things and more like tendencies, inclinations to appear here or there, now or later. Instead of firm answers, nature offers probabilities, like a soft shrug rather than a declaration. At first, physicists thought this strangeness was just a matter of ignorance. Perhaps we simply hadn't built precise enough instruments yet. Perhaps, if we looked closely enough, the world would snap back into something familiar and sensible. But the closer they looked, the stranger it became. Light, for example, behaves in ways that feel deeply contradictory. Sometimes it arrives like a tiny pellet, striking a detector in one precise spot. Other times it spreads out like a wave, passing through multiple paths at once, overlapping with itself like ripples crossing on water. It refuses to choose a single identity. It is not either a particle or a wave, it is somehow both, depending on how it is allowed to move and how it is asked to reveal itself. This is not just a trick of measurement, it is woven into the structure of reality itself. And that raises a quiet but unsettling question. If the basic ingredients of the universe are already blurred and flexible, what else might be less rigid than it appears? For a long time, scientists assumed that reality, at its core, must still be singular. One universe, one unfolding history, one chain of events. The weirdness of the microscopic world was treated like foam on the surface. Strange, yes, but not fundamentally threatening to the idea of a single, continuous reality beneath it all. But some physicists began to wonder if the foam wasn't just surface noise. What if it was a hint of something deeper? What if reality itself is not a single smooth story but a layered one? Not layers stacked dramatically like parallel worlds in science fiction, crashing into each other with sparks and portals, but layers that are so close, so delicately separated, that their presence can only be inferred through the smallest deviations, through patterns that are almost right, through rules that work almost perfectly. In this view, other realities, if they exist at all, would not announce themselves. They wouldn't send messages or open doors. They wouldn't even notice us. Their influence, if any, would be subtle. More like background noise than a signal, more like a faint pressure than a push. Imagine standing in a quiet room where a radio is tuned between stations. You don't hear a song, just a soft hiss. At first it sounds like nothing. But the hiss is made of many distant broadcasts overlapping too faintly to separate. Each one real, each one present, none of them loud enough to claim your attention. Some physicists wonder if parts of our universe behave a little like that radio. When experiments are performed with extraordinary precision, results sometimes show tiny deviations from expectation. Not enough to declare a discovery, not enough to rewrite textbooks, just enough to linger in the margins waiting for better instruments, longer measurements, or deeper theories. These deviations are not mistakes. They repeat. They persist. They remain small but stubborn. And it's in these small places, these nearly invisible corners, that some of the most intriguing questions arise. What if the universe we experience is only one version among many? What if reality branches, overlaps or folds in ways we don't directly perceive? What if the laws of physics we know are not violated but gently nudged by the presence of something nearby? Nearby not in space, as in another galaxy. Nearby not in time, as in the distant past or future, but nearby in a deeper sense, adjacent in the structure of reality itself. Tonight, we won't rush toward answers. Physics, especially at this frontier, doesn't offer certainty. What it offers instead are careful questions built slowly from observation, experiment, and a willingness to accept that the universe may be larger, stranger, and quieter than our instincts suggest. As we continue, we'll explore how these ideas emerge from the foundations of quantum physics, how they scale up to the vastness of the cosmos, and how scientists are learning to listen, not for loud signals, but for the softest of whispers. For now, just rest with the idea that reality might not be broken at all. It might simply be richer than it looks from the surface. And like the calm lake at dusk, sometimes you only notice that richness when you slow down enough to watch the ripples. There is a particular kind of strangeness that doesn't arrive with noise or drama. It arrives quietly, almost politely, and only reveals itself when you look closely enough for long enough. Light is like that. Most of the time, light feels simple. You flip a switch, the room brightens. You open a window, the morning pours in. It travels straight, reflects off surfaces, casts shadows that behave exactly as you expect. Light seems obedient, predictable, and utterly familiar. And yet, when physicists began to ask careful questions about how light behaves at very small scales, it began to tell two very different stories at once. In some experiments, light behaves like a tiny object. It arrives in little packets, striking a detector at a single point, like a grain of sand hitting a drum. Each arrival is localized, precise, and unmistakably particle-like. You can count these arrivals. You can point to where they landed. Everything about them suggests that light is made of discrete individual pieces. But in other experiments, light refuses to behave that way at all. Instead of choosing one path, it spreads out. It flows. It overlaps with itself. It creates patterns of bright and dark, not because something is blocking it, but because parts of light are cancelling or reinforcing one another, the way ripples do on the surface of water. This is not the behavior of a tiny object, it is the behavior of a wave. For a long time, physicists tried to decide which story was the true one. Was light really a stream of particles, or was it fundamentally a wave? But nature, it turned out, was not interested in choosing sides. Light does not switch identities. It carries both stories at once, and which one you see depends on how you allow it to move and how you ask it to reveal itself. A helpful way to imagine this is to picture a calm pond. If you toss a pebble into it, you see ripples spreading outward. Those ripples can overlap, collide, cancel, and amplify one another. Now imagine that instead of tossing one pebble, you release something far smaller, something so small that when it finally reaches the shore, it leaves just one tiny mark. The ripples are wave-like, the arrival is particle-like. Light behaves as if it is doing both at the same time. What makes this especially unsettling is that the wave-like behavior does not disappear just because the arrival is localized. Even when light arrives as a single point, the pattern it creates over time reflects the shape of a spreading wave. Each tiny arrival seems to know something about paths it did not take. This raises a gentle but profound question. When light spreads out like a wave, what exactly is spreading? It is tempting to imagine a physical substance, something vibrating in space, the way sound vibrates air or waves move water. But light does not need a medium. It travels through empty space just fine. There is nothing there to ripple in the usual sense. Instead, physicists describe this spreading as a distribution of possibilities. Light is not committed to one route. It explores many routes at once, not as physical journeys, but as potential outcomes. Before it arrives anywhere in particular, it exists as a range of maybes, each with its own weight, its own influence on the final result. You can think of it like standing at the top of a hill, looking down at a branching network of paths. Before you take a step, all paths are open. Some are steeper, some smoother, some longer. You haven't walked any of them yet, but the shape of the train already matters. When you finally reach the bottom, you will be on one path. But the journey was shaped by the presence of all the others. In experiments with light, this landscape of possibilities leaves its mark. The patterns formed over many trials reveal the invisible structure that guided each individual arrival. The wave-like behavior is not something added on top of the particle-like result. It is what makes that result possible. This dual behavior, localized arrivals guided by spreading possibilities, has been tested again and again in laboratories around the world with astonishing precision. It is not an illusion. It is not a trick. It is one of the most reliable features of the universe at small scales. And yet, it feels deeply counterintuitive. We are used to things being either here or there, now or later, solid or flowing. Light refuses to fit neatly into those categories. It occupies a space that feels almost philosophical, as if nature itself is comfortable holding contradictions that our everyday thinking struggles with. This is where the idea of a wave of possibilities becomes especially useful. Rather than imagining light as switching between identities, it may be better to imagine that the wave is the fundamental description, and the particle-like arrival is how that description becomes concrete when an interaction finally takes place. Before that moment, light is not a thing travelling along a single line. It's a story still being written, with many possible endings coexisting. And this brings us back to the quiet question introduced earlier. If even something as familiar as light does not commit to a single path until it must, what does that say about reality as a whole? Perhaps the world is not built from fixed events marching forward in a single file. Perhaps it is built from overlapping tendencies, gently influencing one another until an interaction draws a line and says, "This is what happened this time." Seen this way, the universe begins to feel less like a rigid machine and more like a fluid process. outcomes are real, but they emerge from a background of alternatives that were also, in some sense, real enough to matter. This does not mean that reality is vague or uncertain in practice. The patterns are precise, the predictions are accurate, the laws work beautifully. But underneath that precision lies a softness, a flexibility, a willingness to explore more than one possibility before settling into a single result. For now, it's enough to let that idea settle gently. Light, the very thing that lets us see, does not simply illuminate the world. It hints at how the world itself may be constructed, out of possibilities first, and certainties second. And as we continue to drift through these ideas, we'll see how this quiet duality opens the door to deeper questions about measurement, choice, and the structure of reality itself. When physicists try to describe what light, or any tiny piece of the universe, is doing before it shows up in one definite place, they often turn to an idea that sounds far more mysterious than it needs to be. They speak of a wave, not a wave of water or air, but a wave of possibilities. It helps to pause here, because this idea is easy to misunderstand if we imagine it too literally. Nothing is physically sloshing through space like an ocean swell. There is no hidden substance filling the room, gently rocking furniture as light passes by. Instead, this wave is more like a map of what could happen. A quiet description of tendencies, a way of saying, here are all the places this particle might arrive, and here is how strongly each place is favoured. Imagine standing in a dark room with a dim lantern. The light does not form a sharp circle with a clear edge. It fades gradually, bright near the centre, softer toward the edges. The glow does not tell you where you must stand, but it tells you where you're more likely to see clearly. In a similar way, the wave of possibilities does not dictate a single outcome. It gently weights the options. Before a particle is detected, it is not secretly hiding in one exact location, waiting to be revealed. According to everything experiments have shown us, it genuinely does not have a single position yet. Instead, it exists in a spread-out state, where many outcomes are allowed to coexist. The wave of possibilities is simply the most honest way physics has found to describe that situation. This can feel unsettling, because we are used to thinking of the world as made of definite things with definite properties. A chair is here, not there. A clock reads one time, not many. But at very small scales, nature seems less interested in committing early. It waits. It allows multiple futures to remain open, right up until an interaction forces a choice. What's important to understand is that this wave of possibilities is not a statement about ignorance. It is not saying, we don't know where the particle is, but it really is somewhere. Instead, it is saying, the particle does not yet belong to a single place in the way larger objects do. The uncertainty is not in our minds. It is built into the situation itself. You can think of it like a story that hasn't reached its ending yet. Before the final chapter is written, many endings are possible. Some would feel natural, others would feel unlikely, but still possible. The wave of possibilities is like an outline of all those endings, with some highlighted more brightly than others. When a measurement happens, when light hits a screen, or a particle triggers a detector, one of those possibilities becomes real in a very concrete way. The particle shows up, a dot appears, a click is heard. From that moment on, there is no ambiguity about what happened. The outcome is sharp and definite, but this sharpness can be misleading. It can make us forget that just moments before, the situation was far richer. Many paths existed, many outcomes were prepared. The final result emerged from a background that was anything but simple. Physicists sometimes describe this process as the wave collapsing. but that word can sound more violent than the reality it describes. Nothing explodes. Nothing breaks. It is more like a decision being finalized. A question that had many acceptable answers suddenly has one answer written in ink instead of pencil. And this brings us to a subtle but important point. The wave of possibilities is not just a mathematical convenience. Its shape has real, measurable consequences. Change the environment and the wave changes. Introduce a barrier and the distribution of possibilities shifts. Alter the available paths and the pattern of outcomes responds accordingly. This is how experiments reveal the presence of the wave, even though we never see it directly. We infer it from the statistics of many events. One particle at a time looks ordinary. Thousands of particles together reveal a pattern that speaks of something underlying, something guiding their behavior long before any single outcome is chosen. It is in this sense that the wave of possibilities begins to feel almost like a quiet landscape underlying reality. Not a landscape of hills and valleys made of matter, but a landscape of likelihoods, gently shaping what can happen and how often it happens. Now, here is where the idea becomes especially interesting in the context of our larger question. If the wave represents many coexisting possibilities, what exactly are those possibilities? Are they just abstract options like imaginary paths on a map? Or do they correspond to something more real, more substantial, even if we never experience it directly? Some interpretations of quantum physics say that these possibilities are nothing more than bookkeeping tools, useful, accurate, but not physically real on their own. Others take a more daring view. They suggest that each possibility is, in some sense, a real branch of reality, unfolding alongside the others until an interaction separates them. We will explore that idea more fully later. For now, it's enough to notice that the wave of possibilities already invites us to loosen our grip on a single, rigid picture of reality. It suggests that what we observe is not the whole story, but the final line of a longer, quieter narrative that plays out behind the scenes. In everyday life, this hidden richness doesn't matter much. A ball still falls when you drop it. Light still turns on when you flip the switch. The universe, at human scales, behaves with comforting reliability. But beneath that reliability lies a framework that is far more flexible than it appears. And perhaps that flexibility is not a flaw or a bug, but a feature. A way for reality to explore many options efficiently, settling on outcomes only when it must. A way for the universe to remain open, creative, and adaptable, even as it produces the stable world we experience. As we continue, we'll see how this idea of many possibilities leads naturally to deeper questions about measurement, branching, and whether the paths not taken truly disappear, or simply continue quietly beyond our view. For now, let the image of the wave rest gently in your mind, not as a technical object, not as an equation, but as a soft field of potential, patiently waiting for the moment when one possibility becomes a lived fact. Up to this point, we've been drifting through a picture of the universe, where possibilities are allowed to coexist quietly, like overlapping shadows at dusk. Nothing is forced to decide too early. Outcomes remain open. Paths remain available. And then, at some point, something happens that brings all that openness to an end. That moment is called a measurement. The word itself sounds simple, almost boring. We measure lengths, temperatures, weights. It feels like a passive act, something we do to the world without changing it. But in the deep language of physics, measurement is anything but passive. It is not merely looking, it is touching. It is interaction, and interaction at the smallest scales carries weight. Imagine walking through fresh snow. Before you step onto it, the surface is smooth, untouched, full of possible paths. The moment your foot presses down, one path becomes real. The snow does not collapse everywhere, it only changes where you touched it. But that change is permanent. The openness that existed before your step is gone in that one place, replaced by a clear record of what happened. Measurement works in a surprisingly similar way. Before a particle is measured, its wave of possibilities spreads gently across many outcomes. But when it interacts with a measuring device, when it leaves a mark, triggers a signal, or produces a detectable effect, one of those possibilities becomes concrete. The interaction does not reveal a hidden answer that was already there. It creates the answer by forcing the situation into a definite state. This is why physicists often say that measurement is not just observation, but participation. The measuring device becomes part of the story. It joins the system it is measuring. Together, they settle on a single outcome from a menu that had been open moments before. A helpful way to think about this is to imagine slicing a loaf of bread. Before the cut, all the slices are still connected. You can talk about where the slices might be, how thick they could be, how many there will be. But once the knife passes through, one slice is separated from the rest. The loaf hasn't vanished. It hasn't exploded. It has simply been divided in a specific way. Measurement is like that knife. It makes a cut through a spread of possibilities, separating one outcome from all the others. What makes this especially interesting is that the cut depends on how the measurement is made. Different measuring setups slice the loaf in different directions. Ask a different question, and you get a different kind of answer. Measure position, and the particle becomes well defined in space. Measure motion, and its position becomes less certain. The universe responds precisely, but not independently of the way you engage with it. This is not a flaw in the theory. It is one of its most carefully tested features. Over and over again, experiments show that the act of measurement changes the situation in a fundamental way. Not because humans are special observers, but because interaction itself is what matters. A measuring device does not need awareness. It only needs to interact strongly enough to force a decision. At this point, it's natural to wonder what happens to the possibilities that were not chosen. Do they simply vanish? Are they erased from existence the moment one outcome becomes real? One way to think about it is to imagine tuning a radio. As you turn the dial, many stations exist at once, overlapping in the background. When you stop turning, one station comes through clearly. The others don't disappear, you're just no longer tuned to them. The act of tuning selects one signal from many. Some interpretations of physics suggest that measurement works in a similar way. The universe tunes in to one outcome, while the others fade from relevance. They no longer influence what we experience. They are, for all practical purposes, gone. But other interpretations ask a more daring question. What if the unchosen possibilities don't disappear at all? What if measurement doesn't destroy them, but simply separates them, the way slicing bread separates one piece from the loaf without destroying the rest? This idea can feel unsettling, because it challenges a deeply held intuition. We like to believe that when something doesn't happen, it truly didn't happen, that the paths not taken are nothing more than imaginary alternatives. But the mathematics of quantum physics does not clearly tell us that those alternatives must be erased. It only tells us that they stop interacting in ways we can detect. From this perspective, measurement becomes a kind of boundary. On one side is the outcome we experience. On the other side are possibilities that no longer influence us directly. Whether those possibilities still exist in some deeper sense is a question physics has not fully answered. What we do know is this: measurement creates a record. Once an interaction leaves a lasting trace on a screen, in a detector, In the environment, it becomes extraordinarily difficult for different possibilities to overlap again. The world at larger scales behaves as if one outcome is decisively won. This is why our everyday experience feels so stable. Tables don't blur, cats don't appear in multiple places at once. The environment itself acts as a vast measuring device, constantly interacting with everything around it. Possibilities are being cut away all the time, leaving behind a clean, consistent story. And yet, at the smallest scales, before those interactions pile up, the richness remains. So measurement is not a magical switch. It is a gradual process, one that begins with interaction and ends with a record. It is the moment where the softness of the quantum world meets the firmness of the world we recognize. Seen this way, measurement is not the enemy of mystery. It is the place where mystery condenses into fact. As we let this idea settle, it prepares us for an even deeper question. If measurement is a cut that separates one outcome from many, what exactly is being separated? And if those other possibilities no longer influence us, where do they go? We won't rush toward an answer. For now, it's enough to notice that measurement is not a simple act of reading information. It is a creative act, one that shapes reality by narrowing it, gently but decisively, from many paths into one. And in that narrowing, the universe reveals both its precision and its restraint, choosing clarity only when it must, and leaving everything else quietly unresolved. Up to now, we've been following a gentle idea that the universe allows many possibilities to exist at once, and that measurement is the moment when one of those possibilities becomes the story we experience. For many physicists, this picture felt almost complete. The wave of possibility spreads, a measurement happens, the wave narrows, one outcome remains, and yet there was always a quiet discomfort hiding inside that explanation. It wasn't about the math. The predictions worked, experiments agreed. The discomfort came from the story we told ourselves about what was happening behind the scenes. The idea that possibilities simply vanish, disappear completely, the moment a measurement takes place, felt strangely abrupt, almost wasteful. As if the universe carefully explored many paths, only to throw most of them away at the last second. In the late 1950s, a young physicist named Hugh Everett asked a simple but radical question. What if nothing ever collapses at all? Instead of imagining the wave of possibilities snapping shut when a measurement happens, Everett suggested that the wave continues smoothly, exactly as it always has. Every possible outcome still exists. The only difference is that those outcomes no longer overlap. They separate. In this picture, the universe doesn't choose, it branches. Imagine standing at a fork in a forest path. In ordinary life, you pick one direction and leave the other behind. But now imagine that the forest itself quietly makes room for both choices. One version of you walks left, another walks right. Each continues on, unaware of the other, surrounded by a world that feels complete and self-consistent. This is the core of what later became known as the many worlds interpretation of quantum physics. In this view, when a measurement occurs, the universe doesn't reduce its options, it multiplies its stories. Every outcome happens, but in a different branch of reality. The wave of possibilities never collapses, it simply unfolds. At first, this idea can sound extravagant. A vast number of worlds constantly branching seems like a heavy price to pay for avoiding collapse. But Everett's proposal wasn't motivated by imagination or spectacle. It was motivated by simplicity at a deeper level. The equations of quantum physics already describe smooth, continuous evolution. Collapse had always been something extra, an added rule, awkwardly stitched on to explain why we see definite outcomes. Remove collapse, and the theory becomes cleaner. The same rules apply everywhere, all the time. No special exceptions, no sudden breaks. What changes is not the mathematics, but our understanding of reality. In a branching universe, the certainty you feel about your experience doesn't come from uniqueness. It comes from isolation. Each branch is so thoroughly separated from the others that it behaves as if it is the only one. Within your branch, events follow a clear sequence. Causes lead to effects. Memories accumulate. The world feels singular, even though it is not. This idea can feel deeply unsettling at first, because it touches something personal. If the universe branches every time a quantum event has multiple outcomes, then there are many versions of you, each living out a slightly different story. Some made different choices, some experienced different accidents, some never existed at all. But it's important to move slowly here and avoid sensational images. These branches are not parallel universes stacked side by side like pages in a book. They do not sit next to each other in space. They do not drift close enough to wave hello. They are separated in a more abstract sense by the structure of the wave of possibilities itself. A useful image is to think of a beam of light passing through a prism. The beam doesn't disappear. It spreads into many colours, each travelling in its own direction. Once separated, the colours no longer overlap in the same way. Each follows its own path, even though they all came from the same source. In the many worlds view, reality behaves like that beam. Measurement is the prism, outcomes diverge. Within any one branch, everything still makes sense. You don't feel yourself splitting. You don't notice the branching. From the inside, your experience is perfectly ordinary. The world still feels stable. Decisions still feel meaningful. The future still feels open, even though, in a broader sense, all futures are unfolding somewhere. At this point, a natural question arises. If these branches exist, why don't they ever interact again? Why don't we see echoes, overlaps, or interference between entire worlds the way we see interference between waves of light? The standard answer is that once branches separate, they become effectively isolated. The differences between them spread into the environment, into countless tiny details. The air molecules move differently. The light scatters differently. Information leaks outward until the branches can no longer overlap in any meaningful way. From then on, they evolve independently. This isolation is not absolute in principle, but it is overwhelming in practice. Like two ink drops spreading in an ocean, once they diffuse enough, there is no practical way to gather them back together. And yet, this answer leaves behind a lingering curiosity. Isolation explains why branches don't interfere in everyday life, but it doesn't prove that interaction is impossible in every circumstance. It simply tells us that interaction, if it exists at all, would be extraordinarily subtle. That subtlety is what makes the idea interesting rather than absurd. If the universe truly branches, and if those branches are not perfectly sealed off at the deepest level, then the influence between them would not appear as dramatic events. It would appear as tiny deviations, as patterns that are almost right, as noise that doesn't quite behave like ordinary noise. This is where the many worlds idea quietly reconnects with our original question. Not, are there other realities, but if there are, could they leave the faintest fingerprints on ours? For now, it's enough to understand the branching picture itself, a universe that never collapses, a reality that doesn't discard possibilities, but allows them to continue, separately and silently. Whether those silent continuations are truly forever beyond reach, or whether they occasionally brush against one another in barely detectable ways, is a question we'll approach carefully without rushing. As you rest with this idea, notice that it doesn't demand belief. It doesn't ask you to imagine portals or meetings or messages. It simply offers a different way of thinking about how the universe handles choice by not choosing at all. Once you allow yourself to imagine a universe that branches rather than collapses, a new kind of quiet question naturally follows. If all these branches exist, each one unfolding its own version of events, are they completely sealed off from one another? Or are they merely almost silent, separated enough that we rarely, if ever, notice? At first glance, silence seems like the safest answer. After all, our everyday experience offers no hint of interference from alternate outcomes. You don't feel the presence of other versions of your life tugging at your decisions. Objects don't flicker between possibilities. The world appears steady, continuous, and comfortably singular. Physics, too, provides strong reasons to expect isolation. As branches form, tiny differences spread outward into the environment. Light scatters in slightly different ways. Air molecules follow different paths. Heat disperses differently. Information leaks into the surrounding world so quickly and so thoroughly that the branches lose any chance of overlapping again. This process happens astonishingly fast, far faster than human senses can follow. A helpful image is to imagine two conversations taking place in a large, echoing hall. At first, the voices are close together, and you might catch fragments of both. But as the speakers move apart, their words fade into separate regions of sound. Eventually, each conversation becomes its own quiet island. Not because the walls suddenly appeared, but because distance and noise did the separating. In this sense, the branches of reality are not locked away behind impenetrable barriers. They simply drift apart into complexity so dense that reconnection becomes practically impossible. But practically impossible is not the same as forbidden by the laws of nature. This distinction is subtle, but important. Physics is full of phenomena that are technically allowed but overwhelmingly unlikely. It is allowed, for example, for all the air molecules in a room to drift into one corner at once, leaving the rest of the room empty. Nothing in the laws of motion forbids it. It just never happens in practice, because the odds are unimaginably small. In the same way, some physicists have wondered whether branches of reality are separated by absolute rules, or merely by overwhelming complexity. If the separation is not absolute, then in principle, under very special conditions, there could be tiny, fleeting interactions between them. Not interactions in the sense of messages or meetings, but something far quieter, a subtle influence, a minute deviation, a whisper rather than a voice. Imagine two radio stations broadcasting at nearly the same frequency. Most of the time, your radio locks onto one station cleanly, but under certain conditions, at night, during a storm, or with a sensitive antenna, you might hear a faint trace of the other station beneath the music. Not enough to identify the song, but enough to know something else is there. Some researchers have asked whether the quantum world might behave in a similar way, whether the outcomes we experience are dominant signals, and whether other branches, if they exist, might contribute the faintest background noise. This idea is not part of the standard interpretation of many worlds. Most versions assume complete silence after branching, but physics has a history of revisiting its assumptions when new tools become available. What once seemed perfectly isolated can later turn out to be weakly connected in ways no one initially expected. It's important to emphasize that this is not a claim, it is a question. A careful, restrained question that arises naturally once branching is taken seriously. If branches were to influence one another at all, that influence would have to be extremely small. Otherwise, we would already have noticed. It would not show up as dramatic violations of known laws. It would show up as tiny discrepancies, patterns that are just slightly off, statistics that lean gently in one direction rather than another. And this is where the idea begins to overlap with the broader theme of our exploration. Not loud disruptions, but subtle fingerprints. Physics already deals with subtlety at this level. Experiments that test quantum behaviour often involve enormous care, isolating systems from noise, vibrations, temperature changes, and stray fields. The goal is to listen for effects that are almost drowned out by the world itself. In that context, the notion of faint cross-branch influence becomes less fantastical. It becomes a question of sensitivity, not spectacle. Still, skepticism is healthy here. Many apparent deviations vanish when experiments are refined. Noise is a constant companion in precision science, and it can be remarkably convincing. The challenge is not finding irregularities, but determining whether they point to new physics or simply to overlooked details. That challenge has shaped how physicists think about branching realities. The emphasis is not on proving their existence through bold claims, but on understanding the conditions under which interaction would even make sense. What kind of influence could survive the rapid spreading of information into the environment? What would it look like mathematically without introducing contradictions? How could it be distinguished from ordinary quantum uncertainty? These questions don't have clear answers yet, but they serve an important role. They keep the theory honest. They prevent imagination from running ahead of evidence. For now, the safest conclusion is also the most modest one. If branches exist, they're extraordinarily quiet. They do not announce themselves. They do not interfere with daily life. Their presence, if it can be inferred at all, would be inferred only indirectly, through careful patterns observed over many experiments. This brings us back to a comforting thought. The apparent silence of the universe is not a failure of curiosity. It may be a feature of how reality maintains stability. Branching allows richness without chaos. It allows many possibilities without confusion, and yet, silence does not always mean absence. Sometimes it simply means that the signal is too soft for the instruments we currently have. As we continue, we'll look at ideas that explore how such softness might still matter, how interactions that are too weak to notice directly could nevertheless shape the behaviour of particles, patterns, and even the large-scale structure of the cosmos. For now, let the question rest gently. Are the branches truly silent, or just very, very quiet? In the quiet hours before sleep, that kind of question doesn't demand an answer. It invites reflection and patience. There is a particular experiment that has quietly unsettled physicists for generations, not because it is complicated, but because it is almost disarmingly simple. It does not require massive machines or extreme conditions. It asks only that we pay attention, patiently, to where a single particle chooses to arrive. Imagine a barrier with two narrow openings, like two doorways cut side by side into a thin wall. On one side, a source releases particles, light particles for example, one at a time. On the other side, a screen waits to record where each particle lands. If particles behaved the way everyday objects do, the outcome would be straightforward. A particle would pass through one opening or the other, and strike the screen directly behind it. Over time, you would see two soft clusters forming, each lined up with one of the openings. Nothing surprising, nothing mysterious. But that is not what happens. Instead, as particles arrive one by one, a delicate pattern begins to emerge. Bright regions appear where many particles land. Dark regions form where almost none arrive. The pattern looks unmistakably like the overlapping ripples you would expect if waves were passing through both openings at once, interfering with one another. And yet, here is the unsettling part. The particles are released individually. There is never more than one particle in the system at any given moment. No neighbours to coordinate with, no crowd to create waves together. Each particle seems to interfere with itself. At first, this feels like a trick of statistics, Perhaps the pattern only emerges when many particles are considered together. But even then, the question remains, how does each individual particle know where the dark regions are? Regions it almost never visits. Even though nothing physically blocks those paths, it behaves as if it is aware of both openings, as if it explores both routes at once, even though it ultimately arrives at a single point. This is where the idea of many paths becomes unavoidable. Before the particle lands on the screen, it does not choose one opening or the other. It behaves as if both possibilities are active. The wave of possibilities spreads through both doorways, overlaps and shapes where the particle is likely or unlikely to arrive. The final dot on the screen is small and precise, but the pattern formed by many such dots reveals a hidden structure, one that reflects paths that were never directly observed. You can picture it like this. Imagine tossing a handful of pebbles into a still pond one at a time. Each pebble makes a small splash, hardly noticeable on its own. But over time, the ripples overlap in consistent ways, creating regions of calm and regions of motion. Even though each pebble lands once, the water remembers the possibility of many overlapping ripples. In the particle experiment, the screen remembers the shape of possibilities. What makes this especially intriguing is that the pattern changes depending on what options are available. If one opening is closed, the pattern shifts immediately. The particle now behaves as if only one path exists. The interference disappears, the bright and dark regions smooth out. This change does not happen because the particle is informed of the closure after passing through. It happens because the landscape of possibilities has changed. The available paths matter, even if the particle does not take all of them in a literal sense. This brings us back to a question we've been circling gently. When a particle behaves as if it has taken multiple paths, what does that really mean? One conservative answer is that the wave of possibilities is simply a mathematical tool, a way to calculate outcomes accurately without implying anything deeper. The particle does not actually travel multiple routes. The wave is just a useful fiction. But there is another way to look at it, one that feels less like bookkeeping and more like a description of something real. In this view, the multiple paths are not imaginary. They are physically relevant even if we only ever experience one result. If that is the case, then the interference pattern becomes something more than a curiosity. It becomes a trace, a kind of fossil record of paths that were available but not chosen but not erased either. This is where the idea of branching realities quietly slips back into the story. If each possible path corresponds to a different branch, then interference begins to look like a memory of those branches before they fully separate. A brief moment when alternatives still overlap enough to shape outcomes. It is important to be careful here. This is not a claim that particles are hopping between universes or communicating across realities. The language of memory is metaphorical, but metaphors can be useful when they help us think clearly without forcing conclusions. What the experiment shows us with extraordinary reliability is that the universe takes all available paths into account before settling on an outcome. The final result is not chosen blindly. It is shaped by the entire landscape of possibilities, and that landscape includes paths that were never directly observed. From this perspective, interference is not a glitch, it is a feature. A sign that reality at small scales is not built from isolated events, but from overlapping potentialities that briefly coexist. As the particle interacts more strongly with its environment, through measurement, through scattering, through entanglement with surrounding systems, those overlapping possibilities lose their ability to interfere. The pattern fades. The world becomes more classical, more definite, more familiar. But before that happens, there is a moment of softness, a moment when many paths are allowed to matter at once. This softness is fragile. It disappears easily. That is why interference experiments require such careful isolation and precision. Any uncontrolled interaction acts like a premature measurement, cutting away possibilities before they can overlap. And that fragility is precisely what makes interference such a sensitive probe of reality's deeper structure. It reveals not what is obvious, but what is almost lost. As we rest with this idea, it becomes easier to see why physicists pay such close attention to these experiments. They're not just demonstrations of strange behaviour, they are windows into how the universe handles choice before it becomes fixed. In the quiet patterns of bright and dark on a screen, we glimpse a world that allows many stories to coexist, briefly, delicately, before letting one take centre stage. And if those stories are real enough to shape outcomes, even for an instant, then it is not unreasonable to wonder whether their influence might occasionally leave traces more subtle still. For now, let the image linger. One particle, many paths. A single mark on the screen, guided by possibilities that were present, even if they were never seen. There is a quiet way to think about interference that doesn't rely on equations or diagrams, but on something far more familiar: memory. Not memory in the human sense of recalling events, but memory as the lingering influence of what could have happened. When we watch a single particle arrive at a screen, we see only one outcome, one dot, one place where the story ends. And yet, as we've seen, the pattern formed by many such dots tells a richer tale. It hints that the particle's journey was shaped by paths it never visibly took. The outcome seems to carry the imprint of alternatives that were present, active, and then quietly set aside. This is why interference can feel so unsettling. It suggests that unchosen possibilities are not irrelevant. They matter, even if they never become the final result. To make sense of this, imagine walking across a field of tall grass. Even if you choose one path, the grass bends and sways around you. Other possible paths, ones you didn't take, still influence how the grass moves, how the air flows, how the field settles afterward. The final trail you leave is shaped by the entire environment, not just the narrow line beneath your feet. In the quantum world, interference seems to play a similar role. The particle's final position is not determined solely by the path it ultimately takes, but by the structure of all the paths that were available to it. The wave of possibilities explores the terrain first. Only later does a single outcome emerge. This way of thinking reframes interference as a kind of shadow cast by unchosen possibilities. Not a literal shadow, of course, but a subtle influence that lingers long enough to shape what happens next. What's important here is restraint. Physics does not demand that we imagine particles consciously considering options or remembering routes. The language of memory is metaphorical. It helps us talk about the influence of alternatives without pretending that particles have minds or intentions. Still, metaphors matter. They shape how we interpret what experiments are telling us. If interference is merely a mathematical artifact, then it is something we tolerate for its usefulness and move past. But if interference reflects the real coexistence of alternatives, however briefly, then it becomes a window into the structure of reality itself. In that light, interference begins to feel less like a technical curiosity and more like a clue. A clue that before the universe commits to one story, it allows many stories to overlap. This perspective becomes especially intriguing when we recall the idea of branching realities. In a branching universe, different outcomes do not cancel one another out. They separate. But before that separation becomes complete, there may be a fleeting period where branches are still close enough to matter. Interference could be the signature of that closeness. Again, this is not a claim. It is a way of organizing our thoughts. a lens through which familiar phenomena take on a slightly different meaning. Physics often progresses by adopting new lenses, not because the old ones were wrong, but because the new ones reveal patterns that were previously hard to see. From this angle, interference is what happens when reality has not yet fully made up its mind. The alternatives are still near enough to overlap, to shape the final outcome together. Once the decision is made, once measurement or environmental interaction steps in, the overlap fades and the branches drift apart. This idea helps explain why interference is so fragile. Any disturbance that marks which path was taken destroys the pattern. It doesn't matter whether a human watches or not. It only matters that information about the path becomes embedded in the environment. Once that happens, the alternatives lose their ability to influence one another. It's as if the universe insists on consistency. It allows ambiguity only up to a point. Once the ambiguity becomes recorded, it is resolved. Seen this way, interference is not a violation of logic, but a careful balancing act. Nature permits flexibility, but only while it remains private. As soon as the world knows too much, through interactions, records and traces, the flexibility collapses into certainty. This balancing act may be one of the deepest features of reality. It suggests that the universe is not purely deterministic, nor purely random, but something more subtle. A system that explores options efficiently, then settles on outcomes that are stable and communicable. And here is where the idea becomes quietly profound. If unchosen possibilities can influence outcomes before separation, then they are not mere abstractions. They are participants, however briefly, in the unfolding of events. This participation does not require that those possibilities persist forever. It only requires that they exist long enough to matter. That thought naturally leads us toward the next step in our journey. If interference reflects the influence of nearby alternatives, could there be situations where alternatives remain near one another longer than usual? Could there be models of reality where separation is not immediate or complete, allowing gentle interactions to continue? Physicists have explored such ideas cautiously and mathematically, proposing frameworks where many worlds exist close together in a conceptual sense, nudging one another just enough to reproduce the behavior we see. We will approach those ideas slowly. For now, it's enough to let interference stand as a reminder that reality's final answers are shaped by questions that linger just beneath the surface. In the soft patterns on a screen formed by countless tiny arrivals, we glimpse a universe that remembers its options, even as it moves on from them. And in that memory, however fleeting, we may be seeing the faint outline of realities that almost were. Up to this point, we've been careful not to rush. We've watched possibilities overlap, separate and fade. We've seen how branching can explain definite outcomes, without forcing reality to make hard choices too early. And we've noticed that interference seems to occur only while alternatives are still close enough to matter. Now, there is a quiet idea that sits exactly at the boundary between these thoughts. It does not ask us to abandon what we already know. It does not ask us to imagine dramatic crossings or messages between worlds. Instead, it offers something far more restrained. It asks a single, careful question. What if nearby realities are not completely indifferent to one another? This idea is known as the many interacting worlds picture. The name can sound bold, even unsettling, so it's important to approach it gently and precisely. This is not a claim about hidden universes communicating or exchanging information. It is a mathematical model, one among several, that tries to describe quantum behavior using a different kind of underlying story. In this picture, the universe is not described by a single wave of possibilities. Instead, It is described as a large collection of individual worlds, each one complete in itself. Each world has particles with definite positions, definite motions, and a clear internal history. Nothing is vague inside a single world. The strangeness arises not from uncertainty within a world, but from how many worlds exist together. You can imagine these worlds as neighbours in a very abstract space. Not neighbours in the sense of houses on a street, but neighbours in the sense of similarity. Worlds that resemble one another closely are considered near. Worlds that differ greatly are far apart. What matters is that these nearby worlds do not sit passively beside one another. They exert a gentle influence, not through messages or signals, but through something more subtle: pressure. A helpful image is to think of a crowd standing shoulder to shoulder. Each person occupies their own space. No one is speaking, no one is coordinating. And yet, the presence of others matters. You feel slight pushes, you adjust your stance. Your position is shaped not only by where you want to stand, but by the presence of those around you. In the many interacting worlds picture, something similar happens. Each world evolves according to ordinary physical rules, but its evolution is nudged by the existence of nearby worlds. These nudges are extremely small. They do not override the laws of motion. They simply add a subtle correction, a gentle tendency that steers outcomes. Importantly, this influence is not communication. No information is exchanged. No world knows anything about the others. The interaction is more like a shared constraint, arising from the fact that many similar worlds exist together. This distinction matters a great deal. Communication implies intention, signalling, and transfer. Pressure implies coexistence. The many interacting worlds idea belongs firmly in the second category. Nothing travels from one world to another. There are no messengers. There is only the quiet effect of proximity. Why introduce such an idea at all? Because remarkably, when the mathematics is worked through, this gentle pressure between worlds can reproduce many of the strange behaviours we associate with quantum physics. Interference patterns emerge naturally. Particles avoid certain regions and favour others, not because a wave guides them, but because nearby worlds collectively shape the landscape of motion. In this picture, a particle's behaviour is influenced by the crowd of similar worlds around it. Where many worlds cluster, motion is subtly redirected. Where worlds are sparse, motion becomes less likely. Over time, the familiar patterns appear. It is crucial to say this clearly and calmly. This model does not claim to be proven. It does not replace existing theories. It does not tell us that other worlds definitely exist. What it offers is something more modest: consistency. It shows that quantum-like behaviour can arise from many definite worlds, interacting gently, without invoking a wave of possibilities that must later collapse. In doing so, it demonstrates that some of quantum physics' strangeness may be explained in more than one way. That alone is valuable. Physics progresses not by clinging to a single story, but by exploring which stories remain coherent under pressure. The many interacting worlds approach survives basic tests of consistency. It does not contradict known experiments. It reproduces familiar results in new language, and yet it remains speculative. No experiment has confirmed that reality is composed of many nearby worlds exerting pressure on one another. No observation has directly revealed such interactions. The idea remains a conceptual bridge, a way of connecting the behaviour we see with a deeper structure that feels intuitive to some and unnecessary to others. What makes it especially interesting for our journey is its tone. This is not a leap into fantasy. It does not ask us to imagine portals or dramatic crossings. It asks us to imagine closeness without contact, influence without exchange. In a sense, it treats reality as something like a tightly packed stack of pages. Each page is complete on its own. Each tells a full story. But the stack as a whole has weight. The pages press against one another, and that pressure subtly shapes how the pages bend, settle, and align. From this perspective, quantum behavior is not mysterious communication between worlds. It is the natural consequence of many similar realities existing together, none of them dominant, all of them contributing quietly to the overall structure. Whether this picture reflects how the universe truly works is still unknown. It may turn out to be a useful metaphor that leads nowhere further, or it may point toward a deeper framework we have not yet fully explored. For now, its value lies in what it teaches us about explanation itself. It reminds us that the same phenomena can sometimes be understood in radically different ways. Waves or crowds, possibilities or neighbours, collapse or pressure. The universe does not tell us which language it prefers, it only tells us what patterns it produces. As we continue, we'll see how this idea prepares us for thinking about barriers, boundaries, and moments when particles appear where they seemingly should not be. Moments where gentle influences might matter more than we expect. For now, let this image settle. Worlds that do not speak, worlds that do not touch, worlds that nonetheless lean against one another, quietly shaping what unfolds. Once you accept the idea of worlds that gently influence one another, a subtle shift takes place in how the universe feels. The focus moves away from dramatic events and singular moments, and towards something quieter and more collective. Reality begins to resemble not a lone traveller choosing a path, but a crowd moving together, each individual step shaped by the presence of others. In the many interacting worlds picture, quantum behaviour does not arise from mystery layered on top of matter. It arises from togetherness, from the fact that many similar realities exist side by side, each complete, each definite, each quietly aware of its neighbours through nothing more than proximity. To make this intuitive, imagine a group of small boats floating on a calm lake. Each boat has its own engine, its own direction, its own destination. No captain communicates with another, and yet, when many boats move close together, the water changes, waves overlap, currents form. A boat may drift slightly off course, not because it chose to, but because the water itself has been reshaped by the presence of others. No messages are sent, no signals are exchanged. Influence arises naturally from coexistence. In this picture, the strange patterns we associate with quantum physics emerge not because particles are uncertain or indecisive, but because they are part of a larger ensemble. Each world follows clear rules internally, but those rules are subtly modified by the presence of neighbouring worlds. Motion becomes a shared phenomenon, even though experience remains individual. This shift in perspective can be surprisingly calming. It removes the need for abrupt transitions or special moments when reality must decide what to do. Instead, everything flows continuously. Worlds evolve. Their similarities and differences shape the overall structure, and from that structure, familiar quantum effects arise naturally. Interference, for example, no longer needs to be imagined as a wave passing through multiple paths at once. Instead, it becomes the visible outcome of many nearby worlds gently steering one another. Regions where worlds cluster become favoured. Regions where they thin out become avoided. Over time, the familiar pattern appears on the screen, not as a mystery, but as a consequence of collective behaviour. It's important to pause here and emphasise restraint. This way of thinking does not claim that the universe truly consists of a vast number of interacting realities. It does not say that this picture is more correct than others. What it says is something more modest and more valuable. that quantum behavior can be explained without invoking collapse, uncertainty, or waves of possibility if we're willing to imagine reality as a dense crowd rather than a solitary line. Physics values such demonstrations deeply. When different frameworks reproduce the same observed behavior, it tells us that the phenomena themselves are robust. They do not depend on a single story being true. They survive translation. At the same time, this abundance of explanations creates humility. It reminds us that what we observe does not uniquely determine what exists. The same patterns can emerge from very different underlying pictures, waves or worlds, possibilities or neighbours. Mathematics allows for more than one consistent narrative. From a bedtime perspective, this is strangely reassuring. It means the universe is not fragile. It does not hinge on a single delicate interpretation. It holds together across multiple ways of understanding, each illuminating a different aspect of the same quiet order. What makes the many interacting worlds idea especially useful for our journey is how it scales. It invites us to think not just about tiny particles, but about systems made of many similar components. It encourages us to see quantum behavior as something that emerges from crowds, not exceptions. This prepares us for the next step naturally. If reality is shaped by proximity and gentle influence, then boundaries become interesting. What happens at the edges of allowed regions? What happens when a particle encounters a barrier? What happens when motion seems forbidden, yet still occurs? In everyday life, barriers are absolute. A wall stops you, a hill slows you, a locked door ends the story. But in the quantum world, barriers are more like suggestions than commands. They reshape motion, but they do not always forbid it entirely. And if we carry the image of nearby worlds with us, barriers begin to look different. They become regions where the crowd thins, where influence weakens, where motion becomes unlikely, but not impossible. This is not yet an explanation. It is a way of preparing the mind, a way of loosening our grip on absolute boundaries and allowing softer transitions to feel natural. Before we move on, it is worth returning to caution one last time. The many interacting worlds picture remains speculative. It has not been confirmed by experiment. It does not replace standard approaches. It is best thought of as a lens, not a verdict. But lenses matter. They shape what questions feel natural to ask next. Seen through this lens, the universe becomes a place where behaviour emerges from togetherness, where subtle influences matter, and where reality does not need to shout to be structured. As the boats drift and the water reshapes itself beneath them, patterns form quietly, without announcement. No single boat creates the wave. No single world creates quantum behaviour. It is the crowd that does the work. And as we drift onward, toward barriers and boundaries, that image will serve us well. It reminds us that what looks impossible from one perspective may simply be unlikely from another, and that gentle influences can sometimes carry us farther than force ever could. For now, let the water settle, let the boats drift, and allow the idea of a universe shaped by nearby realities to rest, softly in the background. There is a moment in physics where intuition quietly gives up its seat. It does not protest, it does not argue. It simply steps aside and lets something stranger take over. That moment arrives when a particle meets a barrier. In everyday life, barriers are firm agreements with reality. A wall stops you, a fence blocks your path, a hill slows you down, and if you don't have enough energy to climb it, you turn back. These rules feel so fundamental that we rarely question them. Motion requires permission, and permission is granted only when conditions are met. But at very small scales, nature treats barriers differently. not as absolute refusals, but as regions of resistance, places where movement becomes unlikely, not impossible. This is where the phenomenon known as quantum tunneling quietly enters the story. Imagine a gentle hill covered in thick fog. You're standing on one side, unsure how steep the climb really is. You don't have enough strength to walk all the way up and over in the usual sense, and yet, because the fog softens the boundary between here and there is a chance, small but real, that you might find yourself on the other side without ever experiencing a clear climb. This image is imperfect, but it captures something essential. In the quantum world, particles are not confined to sharp edges. Their presence fades gradually rather than stopping abruptly. Where a barrier begins, the particle's influence thins like mist creeping into a valley. Because of this softness, there is always a small chance that a particle will appear beyond a barrier, even when classical reasoning insists it should not. This is not teleportation. Nothing jumps instantaneously. There is no violation of cause and effect. Instead, the particle's spread of presence extends into the barrier, becoming weaker as it goes. On rare occasions, that presence reaches far enough to allow the particle to emerge on the other side. What matters most here is not how unlikely the event is, but that it happens at all. Quantum tunneling is not a fringe curiosity. It is essential to the universe as we know it. Without it, the sun would not shine the way it does. At the core of the sun, particles must overcome repulsive forces to fuse and release energy. Classically, they do not have enough energy to do so. Tunneling allows them to slip through that resistance, making stars possible. Closer to home, tunneling plays a role in everyday technology. The delicate behavior of electrons in tiny electronic components relies on their ability to cross barriers they should not, at least according to classical expectations. The modern world hums quietly on this unlikely permission. What makes tunneling especially intriguing is how naturally it follows from the ideas we've already explored. If a particle's presence is spread out, if it exists not as a pinpoint, but as a gentle distribution, then barriers cannot be perfectly sharp. There is always some reach beyond the edge. In the language we've been using, the landscape of possibilities does not stop suddenly at a wall. It tapers, and where it tapers, rare outcomes become possible. Notice how calm this explanation is. There is no need to invoke drama or exception. Tunneling does not break the rules. It obeys them precisely, just in a way that defies our everyday expectations. And yet, that calmness can feel unsettling. It forces us to reconsider what we mean by shouldn't happen. At the smaller scales, shouldn't often means rare, not forbidden. This reframing becomes even more interesting when we recall the idea of nearby realities. In the many interacting worlds picture, a barrier does not completely isolate worlds from one another. Instead, it creates a region where worlds thin out, where fewer nearby realities exist to guide motion in familiar ways. Imagine again the crowd. In an open space, people move freely, gently shaping one another's paths. As the crowd thins near a narrow passage, movement becomes less predictable. Occasionally someone slips through in an unexpected way, not because the passage opened, but because the surrounding influences momentarily aligned. This is only a metaphor. It does not claim that tunneling is caused by neighbouring worlds pushing particles through walls, but it offers a way of visualising why boundaries might feel softer than we expect. The important point is restraint. Quantum tunneling is fully explained within established physics. It does not require additional realities or interactions to exist. Any alternative framing must respect that success. Metaphors are allowed to illuminate, not to replace. What tunneling really teaches us is humility. It reminds us that nature's rules are not written in the language of everyday intuition. They are written in probabilities, tendencies, and gradual transitions. Sharp edges belong to our models, not to reality itself. This lesson carries forward beautifully. Once we accept that boundaries are not absolute, many other strange behaviours become less threatening. The universe begins to feel less like a machine enforcing rigid constraints, and more like a system that negotiates outcomes gently, with room for rare exceptions. As we drift onward, we'll explore an even softer question. If tunneling allows particles to appear where they shouldn't, is there any value in imagining that influence coming from beyond the immediate world we experience? Could metaphors involving neighbours and proximity offer insight, even if they remain firmly in the realm of interpretation? For now, it's enough to rest with the phenomenon itself. Particles slipping through walls, stars shining because resistance is negotiable, a universe that prefers gentle gradients over hard lines, and in that preference, we find not chaos, but a deeper kind of order, one that allows the improbable to happen quietly, just often enough to matter. After spending time with quantum tunneling in its standard, well-tested form, it's important to pause, not to rush forward, but to steady ourselves. Because this is the point where imagination can easily run ahead of evidence if we let it. So we move carefully. Quantum tunneling, as we've seen, does not require any additional realities to exist. It is fully explained within established physics. Particles slip through barriers because their presence is spread out, because boundaries are soft, and because rare outcomes are allowed. Nothing more is needed, nothing extra is required. And yet, once an idea exists, it tends to invite metaphors. If particles can appear where they seemingly shouldn't, and if we've already entertained the picture of nearby realities gently shaping outcomes, then a quiet question naturally arises. Not as a claim, not as a conclusion, but as a thought experiment. What if tunneling could be imagined as a kind of influence from just beyond our immediate world? This framing must be handled with extreme care. It is not a new explanation. It is not a competing theory. It is not something physics currently endorses. It is at most a way of organizing intuition, an image that may help some people grasp why boundaries feel permeable at small scales. Imagine living in an apartment building where the walls are thin. You do not hear conversations clearly. You cannot make out words, but occasionally you notice a vibration, a faint murmur, a subtle shift in the air. Nothing actionable, nothing informative, just enough to remind you that there are other lives unfolding nearby. In this metaphor, tunneling is not a message from next door. It is not information crossing worlds. It is more like a shared vibration, an effect of proximity rather than communication. Again, this is not a claim about reality. It is a way of translating abstract mathematics into a softer mental image. From the perspective of established physics, tunneling occurs because the particle's influence extends into regions that classical intuition treats as forbidden. The probability of finding the particle there fades gradually rather than stopping suddenly. When the barrier is thin enough or the conditions just right, the fading presence reaches through. That explanation is complete and sufficient. The alternative framing simply asks whether the language of nearby worlds could serve as a metaphor for this fading presence. Instead of imagining a single particle stretching through a wall, one might imagine many similar worlds arranged closely together, with some worlds already on the other side of the barrier. Under this imagery, a particle appearing beyond the wall would not feel like a sudden miracle, but like a gentle alignment among neighbours. But we must be absolutely clear. This framing does not add predictive power. It does not explain anything that tunneling does not already explain. It does not allow us to calculate new outcomes or design new experiments. Its value, if it has any, is purely interpretive. Physics often tolerates such interpretations as long as they remain honest about their limits. Metaphors are tools, not truths. They help us think, not decide. And there is a danger here worth naming openly. When metaphors are taken too literally, they harden into beliefs. Suddenly, a helpful image becomes a supposed mechanism. That is not what is happening here, and it is not something we should allow. The phrase, "a whisper from next door," should never be taken to mean that particles are receiving messages from other universes. There is no signaling, no information transfer, no agency. Only the suggestion that influence, in some deep sense, might arise from coexistence rather than direct interaction. In fact, even within speculative models like many interacting worlds, tunneling does not require cross-world nudging. The model reproduces tunneling-like behavior using entirely internal dynamics. No neighbor needs to help a particle through a barrier. The crowd itself shapes the landscape. So why entertain this framing at all? Because science is not only about prediction, it is also about understanding. And understanding often begins with imagery that feels natural to the human mind. Hills, fog, neighbours, crowds. These are ways of translating mathematics into something we can carry with us gently, especially in moments of rest. For someone listening before sleep, the metaphor matters more than the mechanism. It allows the mind to relax without feeling lost. And there is a deeper lesson here, one that transcends tunneling itself. Physics repeatedly teaches us that boundaries are rarely absolute. Whether it is a particle crossing a wall, heat flowing across a surface, or gravity reaching across vast distances, influence tends to leak. Not loudly, not dramatically, but persistently. The universe seems to prefer continuity over separation. That preference does not mean that everything connects to everything else in meaningful ways. It means that reality avoids sharp edges whenever possible. It smooths transitions. It allows gradients. It tolerates rare exceptions. Seen through that lens, the metaphor of a whisper is not about other worlds at all. It is about the character of nature, a nature that allows influence without announcement, change without rupture, and motion without certainty. As we prepare to move outward, from laboratories to the sky, this lesson will stay with us. The same softness that allows tunneling at small scales may also shape how entire universes relate to one another, if they exist at all. But we will not rush there. For now, it's enough to sit with the distinction. Tunneling is real, tested, and essential. Alternative framings are optional, gentle and speculative. They do not compete with physics. They accompany it, like quiet music beneath a steady narration. If there are whispers in the universe, they are not voices calling out to us. They are reminders that boundaries are suggestions, not commandments, and that reality is often more generous than our first instincts allow. And with that thought resting softly in the background, we are ready to lift our gaze, slowly, from the smallest scales toward the vastness of the cosmos. As we slowly lift our attention from particle and laboratories to the universe as a whole, it helps to carry one quiet lesson with us. Boundaries in nature are rarely as firm as they appear. They feel solid from the inside, but they are often defined by limits of reach rather than walls of exclusion. Nowhere is this more true than at the largest scale we can imagine. Look up at the night sky, and it feels infinite. Stars scatter outward in every direction. Galaxies fade into darkness without any visible edge. It is tempting to believe that what we see is simply a small part of something endlessly vast. In a sense, that intuition is correct. But the reason we cannot see farther is not only distance, it is time. Light, even moving at its extraordinary speed, takes time to travel. When we look across space, we're also looking backward. Nearby stars appear as they were years ago. Distant galaxies appear as they were billions of years ago. The deeper we look, the younger the universe becomes. Eventually, we reach a limit, not because the universe ends there, but because light from beyond that point has not had enough time to reach us since the universe began expanding. This limit is called the cosmic horizon. It is best not to imagine the cosmic horizon as a wall or a shell. Nothing special happens there. No barrier is struck. No edge is encountered. It is simply the boundary between what has had time to influence us and what has not. A helpful image is to imagine standing in a vast fog-covered landscape at dawn. As the sun rises, the fog slowly thins, revealing more and more of the terrain. The edge of your visibility is not the edge of the land. It is the edge of what light has revealed so far. The universe is like that landscape. The cosmic horizon is not a fence. It is the current reach of illumination. Beyond that reach, there may be more galaxies, more structures, more events unfolding quietly. Or there may be something entirely different. Physics does not currently know. What matters is that beyond the horizon does not mean nothing. It means not yet observable. This distinction is gentle but profound. Everything we have learned about the universe is based on what lies within this visible bubble. Our theories, our measurements, our maps of cosmic structure all apply to the region that has been in contact with us through light, particles, or gravity. But physics also allows for the possibility that the universe extends far beyond this bubble, perhaps endlessly. If so, then our observable universe is not the whole story. It is a region shaped by a shared history, a common beginning, and a finite exchange of influence. This idea fits naturally with the themes we've been exploring. Just as particles' behavior is shaped by the paths available to it, the universe we observe is shaped by the regions that have had time to interact with us. What lies beyond remains part of reality, even if it does not yet participate in our story. And here, a quiet analogy returns. The cosmic horizon is like the edge of hearing. Sounds beyond a certain distance still exist, but they do not reach you. They do not influence your experience. For all practical purposes, they are silent, yet silence is not absence. From this perspective, the observable universe becomes a kind of bubble, a region defined not by physical boundaries but by causal contact. Everything inside has in some way been able to exchange information since the universe began expanding. Everything outside has not. This image becomes especially important when we begin to think about larger frameworks of cosmology. Some theories suggest that the process that created our universe did not happen just once. Instead, it may still be happening elsewhere, giving rise to many such bubbles, each expanding, each carrying its own internal history. We will approach those ideas carefully. For now, it is enough to understand the role of the horizon itself. The horizon explains why the universe appears the way it does. It explains why the distant cosmos looks remarkably similar in all directions. It explains why there is a limit to how much information we can gather, no matter how powerful our instruments become. And it also teaches a kind of humility. There may be regions of reality that are just as real as ours, governed by the same laws or perhaps slightly different ones that simply lie beyond our reach. Not hidden by intention, but separated by time. In the quiet tone of bedtime reflection, this can feel surprisingly comforting. It means the universe does not end where our knowledge does. It continues patiently beyond the boundaries of our perception. As we drift outward in imagination, from particles to stars to the very edge of what we can see, the same pattern repeats. Reality offers us a window, not the entire landscape. What we observe is shaped by what can reach us, not by what exists. This prepares us gently for the next step. If our observable universe is one bubble among many possible regions, then the early moments of cosmic history become especially interesting. They may carry traces of interactions, overlaps, or collisions that happened long before the universe became calm and transparent. But we will not jump ahead. For now, rest with the image of the cosmic horizon as a soft boundary, a limit defined by time and light, not by walls or endings, a reminder that the universe we see is vast, but not necessarily complete. And just as with quantum boundaries, the edge of what we can see is not a denial of what lies beyond. It is simply an invitation to wonder, quietly and patiently, about a reality that continues unfolding outside our view. Once we accept the idea that our observable universe is defined by what has had time to reach us, a natural curiosity arises. If there is more beyond our visible bubble, how did our bubble come to be in the first place? And could there be others forming elsewhere, quietly and independently? To approach this, we return to the earliest moments of cosmic history, to a time when the universe was not calm and transparent, but young, energetic, and rapidly changing. According to modern cosmology, the universe experienced an early period of extraordinary expansion. Space itself stretched quickly, smoothing out irregularities and setting the stage for everything that followed. This expansion did not push matter through space like an explosion. Instead, it expanded the space between things, carrying matter along gently, the way dots on a balloon move apart as the balloon inflates. In some theoretical pictures, this expansion did not happen just once and then stop everywhere. Instead, it may still be happening in distant regions, even now. Space continues to expand rapidly in some areas, while slowing down in others, forming pockets where expansion settles into a calmer, slower growth. Each of these pockets can be imagined as a bubble. Inside a bubble, the universe behaves much like ours does today. Galaxies form, stars ignite, time unfolds in a familiar way. Outside the bubble, expansion continues so rapidly that structures cannot form in the same manner. The bubble becomes a self-contained region with its own internal history. The soap bubble metaphor is useful here, as long as we use it gently. Imagine a pot of water beginning to boil. Small bubbles form, grow, and separate from one another. Each bubble has a surface, an interior, and a distinct life of its own. The water around them continues to churn, giving rise to new bubbles elsewhere. In the cosmic version of this image, each bubble is a universe. Not a universe floating in space, but a region of space itself where conditions have settled enough for familiar physics to unfold. Importantly, these bubbles are not popping in and out of existence in dramatic bursts. They form early, long before stars or planets exist. They expand, they cool, and over vast stretches of time, they become places where complexity can arise. If this picture is even partly accurate, then our observable universe may be just one such bubble among many. This idea can sound extravagant, so it's important to keep the tone grounded. Bubble universes are not something we observe directly. They're not required by all theories. They arise naturally in certain models of cosmic expansion, but they remain speculative. What makes them interesting is not the number of bubbles, but the possibility of interaction in the distant past. If bubbles form in a shared expanding background, then it is possible, at least in principle, that some of them may have brushed against one another early on. Not violent crashes, not ongoing chaos, but brief encounters in the universe's infancy before everything had time to settle. These encounters, if they happened, would be ancient beyond comprehension. They would not be happening now. They would have occurred long before the first atoms formed, long before light could travel freely through space. And yet, their effects might linger. Imagine two soap bubbles touching briefly before drifting apart. The point of contact leaves a subtle distortion, a flattened region, a slight asymmetry. Long after the bubbles separate, that gentle scar remains. In cosmology, researchers have asked whether something similar could exist in our universe. If our bubble once encountered another, could that interaction have left an imprint? Something faint, something subtle, in the structure of space itself. The key word here is subtle. Any such imprint would not announce itself as proof of another universe. It would not appear as a clear signal with a label attached. Instead, it would appear as a small irregularity, a region that looks slightly different from its surroundings, a pattern that feels just a little out of place. This brings us to the idea of cosmic humility again. Even if we were to observe such irregularities, interpretation would be difficult. The early universe was a complex place. Many processes could leave similar marks. Distinguishing between them requires extraordinary care. So physicists proceed cautiously. They do not claim evidence, they explore possibilities. What matters for our journey is not whether bubble collisions definitely happened, but how the idea fits into a broader pattern. Again and again, we see the same theme. Reality at large scales, like reality at small scales, may consist of many regions that evolve mostly independently, but not necessarily in perfect isolation forever. Just as quantum possibilities overlap briefly before separating, cosmic regions may have interacted briefly before drifting apart across expanding space. The echo of that interaction, if it exists at all, would be incredibly faint. It would be woven into the oldest observable light, stretched and softened by billions of years of cosmic expansion. And that thought brings us naturally to what we will explore next. The universe carries with it a kind of memory, not a conscious memory, but a physical one. The early conditions of the cosmos are recorded in subtle patterns that still surround us today, if we know how to listen. As we prepare to turn our attention to that ancient light, it helps to remember the tone we've maintained throughout. No leaps, no declarations, only careful curiosity. Bubble universes, if they exist, do not diminish the meaning of our own. They do not make our story less real. They simply remind us that reality may be larger, older, and more intricate than any single window can reveal. For now, let the image of bubbles drifting in an unseen sea rest quietly in your mind. Not as fact, not as fantasy, but as one of many ways physicists attempt to describe a universe that may be richer than it appears. There is a kind of photograph the universe carries with it. Not an image made of paper or pixels, but a faint glow that fills all of space, arriving gently from every direction. It is so subtle that we do not notice it with our eyes, and so ancient that it began its journey long before any star, planet, or living thing existed. This glow is often described as the universe's baby picture. In the earliest moments after the universe formed, everything was hot, dense, and opaque. Light could not travel freely. Space was filled with charged particles constantly scattering radiation, making the universe more like a thick fog than an open sky. Nothing could shine clearly. Nothing could be seen. Then, after hundreds of thousands of years, the universe cooled enough for matter to settle into stable forms. Charged particles combined into neutral atoms. Suddenly, light was no longer trapped. It could travel freely through space, carrying with it a snapshot of the universe at that moment. That ancient light has been travelling ever since. Today it reaches us as a faint uniform background, stretched and softened by billions of years of cosmic expansion. It does not appear as visible light, but as a gentle warmth, detectable only with sensitive instruments. And yet, despite its softness, it carries an extraordinary amount of information. This background glow is remarkably smooth. Wherever we look, it appears almost the same. That smoothness tells us something profound. It tells us that the early universe was astonishingly uniform, balanced, and calm on large scales. But almost the same is not the same as exactly the same. Tiny variations are present. Minuscule differences in temperature and intensity ripple across this ancient light, forming patterns so delicate that they took decades of careful measurement to reveal. These variations are not noise, they are structure. They are the seeds from which galaxies eventually grew. And they are also where curiosity lingers, because embedded within this oldest light are features that feel slightly unusual. There are regions that appear a little cooler than their surroundings, areas where the pattern seems subtly asymmetric. Nothing dramatic, nothing that breaks the laws of physics, just small irregularities that invite careful attention. One of these features is often referred to as a cold spot. It is a region where the background glow appears slightly less warm than expected. On its own, this is not alarming. Random variations can and do occur. The universe is not perfectly smooth. What makes such features interesting is not their existence, but their context. Physicists ask whether these irregularities fit comfortably within our best models of cosmic evolution, or whether they might hint at something more. This is where the idea of ancient interactions returns quietly to the conversation. If our observable universe were once part of a larger, more complex environment, if it formed as a bubble among others, then the earliest moments of its existence may have involved brief encounters or influences from beyond what we now see. Any such interaction would not leave clear signatures. It would not carve messages into the sky. It would leave only the gentlest of marks, softened by time and expansion. Like a bruise fading on old skin, its edges blurred, its origin difficult to trace. Physicists approach these possibilities with humility. The early universe was a dynamic place. Many processes can produce similar patterns. Density fluctuations, quantum variations stretched across space, and later cosmic effects can all shape the background light in subtle ways. Distinguishing between these possibilities is extraordinarily difficult. That difficulty is not a failure. It is a reflection of how cautious science must be when dealing with events that occurred nearly 14 billion years ago. There is no experiment we can rerun. There is no controlled environment. There is only careful observation and patient interpretation. So when scientists study these ancient patterns, they do not ask, does this prove another universe exists? They ask something gentler and more precise. Does this feature fit naturally within what we already understand, or does it invite us to consider additional possibilities? Even when anomalies persist, they are treated not as evidence, but as questions. This attitude is worth lingering on. In popular imagination, unusual cosmic features are often framed as revelations waiting to happen. But in real science, they are reminders of uncertainty. They signal where understanding may deepen, not where conclusion should harden. The oldest light in the universe does not speak in sentences, it whispers in statistics. Every interpretation must be tested against alternatives, every pattern must be weighed against chance. And every speculative idea must survive the discipline of skepticism. In the context of our journey, these faint irregularities serve a different purpose. They remind us that the universe carries a long memory. Events from its earliest moments still echo softly through the present, not as stories we can read clearly, but as textures we can feel. Whether those textures point to bubble collisions, ancient influences, or simply the natural richness of cosmic evolution remains open, and that openness is part of the beauty. For someone listening in the quiet hours before sleep, the message here is not one of mystery demanding resolution. It is one of scale and patience. The universe has been unfolding for an unimaginably long time, It has room for complexity, for subtlety, and for questions that remain unanswered without diminishing what we already know. The oldest light does not tell us everything, but it tells us enough to know that our universe has a history deeper than our stories and a structure gentler than our expectations. As we continue, we will move from listening to ancient echoes toward considering how we might listen more carefully in the future, not by expecting dramatic signals, but by refining our sensitivity to the smallest deviations. For now, let the image of that ancient glow rest softly in your mind, a quiet presence, filling space, carrying whispers from a time when everything was young, and the universe was just beginning to remember itself. As our attention drifts from ancient light toward the deeper structure of reality itself, it helps to release one habit of thought. We often imagine more as meaning farther away, more space, more distance, more emptiness stretching outward. But physics sometimes asks us to imagine something very different, more folded. To understand this, picture a piece of fabric resting on a table. From a distance, it looks flat and simple, left to right, front to back. But if you lean closer, you begin to notice folds, wrinkles, and layers stacked gently on top of one another. The fabric has depth that is not obvious at first glance, directions that exist but are hidden in the folds. Some theories suggest that our universe may be like that fabric, not larger in the sense of endless open space, but richer in structure than we immediately perceive. In addition to the familiar directions, forward and back, left and right, up and down, there may be additional directions folded so tightly that we never move through them in everyday life. These are often called extra dimensions, but that phrase can sound more dramatic than it needs to be. It does not mean secret corridors or alternate places we could visit if we found the right door. It means directions of motion that exist mathematically and physically, but are compressed to scales so small that they remain invisible to us. A helpful image is to imagine a tightrope. From far away it looks like a one-dimensional line. You can walk forward or backward, that's it. But if you zoom in closely, you see that the rope has thickness. You could move around its circumference, but that motion is so small compared to its length that it doesn't matter for walking across it. In this picture, extra dimensions are like the thickness of the rope, present, real, but hidden by scale. Building on this idea, some models suggest that our entire universe might be confined to a kind of surface within a higher dimensional space. This surface is often described as a brain, not a world floating in space, but a region of space itself, shaped and embedded within something larger. On this surface, all the familiar forces and particles exist. Light travels, matter interacts, atoms form, life unfolds, everything we experience happens here. Beyond this surface, there may be additional dimensions we do not normally access, not because they are forbidden, but because the ingredients of our world are bound to the surface itself. This is where the fabric metaphor becomes especially useful. Imagine embroidery stitched into cloth. The pattern exists on the surface. It has richness, colour and structure, but the cloth itself extends beyond the pattern. You could fold the cloth, layer it, bring distant parts close together without the pattern ever noticing. In some theories, our universe is like that pattern. Most forces, those responsible for holding atoms together and shaping chemistry, are confined to the surface. They do not wander off into the surrounding space, but one force behaves differently: gravity. Gravity is exceptionally weak compared to the other forces. It spreads out. It refuses to stay neatly contained. This has led physicists to wonder whether gravity might be able to reach into those hidden dimensions, leaking gently away from our surface into the surrounding space. If that were true, it would help explain why gravity feels so faint. It is not weak because it lacks strength. It is weak because it is shared. Like sound spreading into a large room, its influence thins as it reaches into directions we cannot see. This idea is speculative, but mathematically consistent. It does not require tearing holes in reality or inventing new particles for dramatic effect. It simply rearranges where familiar forces are allowed to travel. And once again, caution is essential. These ideas have not been confirmed. They are frameworks, not findings. They guide research. They suggest possibilities. They do not declare truths. One intriguing side note often mentioned in this context involves dark matter. Dark matter is a name we give to something that seems to exert gravitational influence without emitting light or interacting in familiar ways. We infer its presence from how galaxies rotate and how large structures hold together. Some have wondered whether dark matter could be ordinary matter existing on a nearby surface, a neighbouring layer of the same fabric, interacting with us only through gravity. This is an elegant idea, but it remains speculative. There are many competing explanations, and none has yet been confirmed. It is important not to let elegance replace evidence. Still, the layered fabric picture offers something valuable, even if it turns out not to describe reality exactly. It trains the mind to think beyond simple emptiness. It suggests that space itself may have structure, thickness, and depth beyond what we immediately perceive, and it does so without requiring drama. No portals, no collisions in the present day. No hidden civilizations tucked just out of sight, only a quiet rearrangement of how space might be organized at the deepest level. In the context of our larger journey, this fits beautifully. Again and again, we encounter the same theme. Reality may be larger, richer, and more layered than our experience suggests, yet still gentle, stable, and lawful. Extra dimensions, if they exist, do not intrude into daily life. They do not disrupt causality. They do not undermine meaning. They simply provide a deeper backdrop against which familiar processes unfold. As we approach the final stretch of our exploration, the emphasis shifts once more, from what might exist to how we might notice it, if at all. If reality has hidden layers, neighbouring regions or folded directions, we will not discover them through spectacle. There will be no sudden revelation, no moment when the sky opens and answers pour out. Discovery, if it comes, will arrive quietly, through patience, through precision, through noticing the smallest deviations from expectation. And that brings us naturally to the next stage of our journey, how science listens, not for voices or signals, but for the faintest murmurs in the fabric of measurement itself. For now, let the image of layered fabric rest in your mind. Space not as emptiness, but as texture. Reality not as a single sheet, but as a cloth folded in ways we are only beginning to imagine. After wandering through particles, boundaries, bubbles, and folded layers of space, it's natural to wonder how any of this could ever move beyond imagination. If realities overlap quietly, if dimensions hide in folds, if ancient interactions left only the faintest marks, how could science possibly notice? The answer is gentler than you might expect. Science does not wait for voices from the sky. It does not look for messages or announcements. It listens for deviations. Most of the time, the universe behaves with remarkable consistency. Atoms vibrate as expected. Light travels as predicted. Clocks tick with astonishing regularity. This reliability is not boring. It is essential. Without it, we could not build theories, test ideas, or trust measurements. But it is precisely this consistency that makes deviations meaningful. A deviation is not a dramatic event. It is a whisper in the data, a result that is just slightly off, a pattern that does not quite line up with expectations, even after every known explanation has been carefully considered. This is how science has always advanced. Not by chasing spectacle, but by refining attention. Imagine listening to a familiar piece of music played on a well-tuned instrument. You know every note, every pause. If one string is slightly out of tune, you may not notice it at first. But as you listen more carefully, something begins to feel wrong. Not loud, not obvious, just unsettled. Physics listens in the same way. If hidden layers of reality exist, extra dimensions, neighbouring regions, subtle interactions between worlds, they are not expected to announce themselves directly. They would influence outcomes only faintly. They would alter probabilities by tiny amounts. They would introduce minute discrepancies that reveal themselves only through patience and precision. This is why many of the most ambitious experiments in modern physics look almost quiet from the outside. Consider precision clocks. Some of the most accurate clocks ever built lose or gain less than a second over the entire age of the universe. They are so stable that even tiny shifts in gravity, motion, or environmental conditions can be detected through their ticking. By comparing such clocks in different locations, scientists can test whether time itself behaves exactly as expected, or whether something subtle is nudging it. Then there are interference experiments, variations on the same delicate setups we discussed earlier, refined to extraordinary levels of control. Here, scientists look not for new patterns, but for the slightest distortions in familiar ones, a fringe that shifts imperceptibly, a distribution that leans just a little more than predicted. Gravitational waves offer another quiet listening post. These gentle ripples in the fabric of space itself, produced by massive events like merging black holes. By studying their shape, timing, and dispersion, physicists can test whether gravity behaves exactly as our current theories predict, or whether it leaks, bends, or fades in unexpected ways. What matters most is the mindset behind these efforts. Science, at its best, is not impatient. It does not demand immediate answers. It builds instruments capable of noticing what is almost unnoticeable, then waits. Sometimes years pass without anything surprising happening, and that too is information. It tells us which ideas are constrained, which possibilities remain viable, and which directions may be less promising. This approach is especially important when dealing with ideas as speculative as multiple realities or hidden dimensions. The burden of proof is high, and rightly so. Extraordinary claims are not rejected outright, but they are held at arm's length until evidence earns their trust. That evidence, if it ever arrives, will not look like a revelation. It will look like a discrepancy that refuses to go away. A measurement that improves and improves, yet remains slightly inconsistent. A result that survives cross-checks, refinements, and skepticism. A quiet persistence that slowly shifts confidence. This is not the kind of discovery that makes headlines overnight. It is the kind that reshapes understanding over decades, and there is something deeply calming about that. In a world that often rewards speed and certainty, science reminds us that truth unfolds slowly, that patience is a virtue, that listening can be more powerful than shouting. From the perspective of a listener resting before sleep, this is perhaps the most human part of the story. The universe is not hiding secrets out of spite. It is simply subtle, and subtlety requires care. If reality has layers beyond our perception, they will not be revealed through force or insistence. They will reveal themselves, if at all, through the smallest inconsistencies, noticed by minds willing to sit quietly with uncertainty. As our journey approaches its end, this idea prepares us for a final reflection. Whether or not other realities exist, whether or not hidden dimensions shape our universe, the way we seek understanding matters. We do not stand outside the universe, demanding answers. We are inside it, listening carefully to its rhythms, and sometimes the act of listening is itself the reward. As our journey comes gently to rest, it may help to return to the mood we began with. Not urgency, not answers, but quiet curiosity. Throughout this exploration, we've drifted from the smallest scales of particles and possibilities to the widest reaches of cosmic history. Along the way, we've encountered ideas that stretch the imagination, branching outcomes, neighbouring realities, ancient bubbles, folded dimensions. None of them demanded belief. None of them offered certainty. Instead, they asked something simpler and more human. They asked us to consider perspective. What if the reality we experience is not the whole story, but a slice? Not a false slice, not an illusion, just a partial view, shaped by what can reach us, what can influence us, and what we are able to measure. Imagine standing in a quiet room with a single window. Through that window, you see a landscape, trees moving softly in the wind, clouds drifting slowly overhead. The view is real, it is accurate, it tells you something true about the world outside, but it is not the entire landscape. There are hills beyond the frame, rivers you cannot see, details unfolding behind your back. None of these diminish the reality of what you observe. They simply remind you that observation is always framed. Physics has been teaching us this lesson gently for more than a century. At small scales, particles do not commit to single stories until interaction forces them to. At large scales, the universe we see is limited by time, light, and cosmic history. What we experience is shaped not only by what exists, but by what can reach us. Seen this way, the idea of other realities intersecting ours does not feel threatening or destabilizing. It feels almost natural, a continuation of the same pattern, reality revealing itself layer by layer, never all at once. And within that pattern, something important remains unchanged. You are still here. Your experiences still matter. Your choices still carry meaning. Even if the universe is vast beyond comprehension, even if countless possibilities unfold beyond your awareness, the story you inhabit is not diminished. It is defined. Meaning does not require exclusivity. A moment does not lose its value because other moments exist elsewhere. A life does not become insignificant because the universe is large. If anything, the opposite may be true. Living inside a thin slice of something larger gives each moment a certain clarity, a focus. We experience one outcome, not because others are impossible, but because this is the thread we follow. This is the melody we hear, even if countless harmonies surround it quietly. Questions about identity often surface here. If there are many versions of reality, which one is truly you? But perhaps that question assumes something unnecessary. Perhaps identity is not about being the only version. Perhaps it is about continuity, the unbroken experience of moving from one moment to the next within a single story. From the inside, your story is whole. Time, too, takes on a softer meaning. Whether time emerges from deeper laws or flows as we experience it, it remains the medium through which meaning unfolds. We remember, we anticipate, we reflect. These are not illusions, they are the texture of being alive. The universe may be layered, branched, or folded in ways we do not yet understand, but it still allows for memory, for care, for wonder. It still allows for quiet moments before sleep, when questions drift without demanding answers. And perhaps that is the most important lesson of all. Science does not strip the universe of mystery. It refines it. It transforms fear into curiosity, and curiosity into patience. It teaches us how to sit with not knowing, without rushing to fill the silence, whether future discoveries reveal hidden dimensions, interacting realities, or simply confirm the elegance of what we already know. The act of listening remains the same, careful, humble, open. As you rest now, you don't need to hold on to every idea we've explored. Let them fade gently, like distant lights seen through mist. What remains is a feeling rather than a conclusion, a sense that reality is deeper than it looks, a sense that boundaries are softer than they seem, a sense that your place within it is both small and complete. You're not required to understand the whole universe to belong to it, and so, as the questions settle and the mind grows quiet, you can let go of the need for answers. The universe will continue unfolding with or without our certainty. For now, it is enough to have listened, enough to have wondered, enough to have rested briefly inside this thin slice of something vast.